The discovery unveiled by the James Webb Space Telescope has sent shockwaves through the world of physics, shattering long-standing debates with a single breathtaking image. Imagine a scene where decades of speculation and argumentation suddenly meet their match in a vivid portrait captured by this revolutionary telescope. No longer are we left to ponder. The Webb Telescope's latest revelation stands as a monumental game-changer that promises to reshape our understanding of the cosmos. At the heart of this revelation lies one of astrophysics' most contentious issues, the enigma surrounding the age and expansion rate of the universe. For generations, scientists have grappled with conflicting measurements of the Hubble constant, the cosmic speedometer that reveals how rapidly our universe is growing. On one side, local measurements using celestial benchmarks like Cepheid stars and supernovae point to a universe expanding briskly. Yet, observations of the cosmic microwave background, CMB, the lingering afterglow of the Big Bang, suggest a slower pace. These divergent findings have spurred intense scrutiny and a flurry of studies aimed at deciphering this cosmic conundrum. Are we witnessing the emergence of new physics, or could discrepancies stem from methodological oversights? The pursuit of answers has never been more urgent, propelled by the stark realization that our current understanding may be incomplete. The Webb Telescope's profound contribution lies not just in its ability to capture stunning cosmic imagery, but in its role as a catalyst for scientific breakthroughs. This newfound clarity offers a glimpse into the intricate workings of our universe, beckoning us to explore deeper, question further, and embrace the exhilarating uncertainty that defines the frontier of cosmology. We can see farther into the darkness of space than ever before, thanks to the James Webb Space Telescope. Because of what it can do, the telescope can show us elements, planets, and galaxies that we would not have thought were possible to see. Scientists naturally thought that information from Webb would help them figure out the Hubble constant more accurately. The first wave of data, on the other hand, has made things a lot more difficult. They've taught us new things that don't fit with what we thought we knew. Could this information help us come up with a new idea about space that changes the way we think about it? If so, we might need to think again about what we know about how the universe works. For example, we might find particles and forces that have never been seen before. Or it could mean that dark energy, the unknown force that is speeding up the growth of our universe, needs to be looked at again. As we keep finding new things, our ideas about space have changed over time. One example is the cosmic microwave background radiation that scientists found in 1965. It was strong proof for the Big Bang theory. Before that, scientists thought the universe would last forever, which meant it would keep growing at the same rate. However, the new proof showed that wasn't true. Also, when we learned near the end of the 1990s that the universe was growing all the time, we learned about dark energy and how it affected the expansion. So whenever we learn something new, we check to see if it fits with what we already know and come up with new ways to understand the universe better. Because of this, the problem we're having in cosmology right now could lead to finding the best ways to fix the universe. Although the problem is difficult, it is also exciting because it pushes us to make better tools for exploring space. Scientists from all over the world are interested in this cosmological problem because they all want to know more about the universe. The most important thing is that it shows how science is always growing and changing as we learn more about space. The S8 tension is another worry that goes along with the Hubble tension. This is about how matter is spread out in space. In the world, you can use this to make a structure of the world and see how it has changed over time. This is called lumpiness by scientists because some parts of space have a lot of galaxies close together and other parts don't have many. Different methods will be used by the scientists to find out how big this lumpiness is. A possible answer is to look at how the different densities of big things like galaxy groups bend light from galaxies far away. Gravitational lensing is the name for this bending. It lets us look into where dark matter is, since it doesn't give off light and is therefore undetectable. Scientists also use the cosmic microwave background, CMB, which is a glow left over from the Big Bang. This light has been moving for about 13.8 billion years, carrying messages from the beginning of the world. Scientists can figure out how the universe was lumpy when it was first created by analyzing the CMB. This should match how the universe is observed to be lumpy right now on a large scale. But there's a catch. These numbers don't match up either. The lumpiness of the CMB, which is shown by the non-spherical gravity distribution model, suggests that the early universe's matter distribution was more even than what was seen with gravitational lensing. We can guess that there is something else we are not taking into account in the interpretation. This takes us back to the idea of dark matter. What does dark matter really mean, and how does it work? The question still hasn't been answered though, but there is still hope. The James Webb Space Telescope will change the field of astronomy with its camera sensitivity and clarity that have never been seen before. The telescope will look into the early times of the universe and find out how the first galaxies and stars came to be. This lets us get better measures of how the universe is expanding and how matter is spread out. In order to answer these important questions, we will need to carefully observe things and maybe come up with new theoretical methods. Finding out more about dark energy, learning completely new physics, or even just getting a better idea of how dark matter behaves will have huge effects on many areas of life. Trying to figure out the mysteries of the world is like putting together a zillion-piece puzzle while wearing blindfolds. Scientists are like thorough detectives who are concerned with figuring out what's going on. Project Flamingo, NASA's newest effort, shows that the agency is becoming more and more interested in scientific exploration. Project Flamingo is a huge step forward in computer science. It uses one of the most famous supercomputers in the world, which is located at Durham University in Britain. It takes more than 50 million computer hours to make and has 30,000 processors and more. The activity shows that scientists are determined to study the whole universe with a main focus on dark matter, the strange substance that doesn't give off, absorb, or reflect light, but is thought to exist because it pulls visible matter together. Scientists are still puzzled by how hard to find it is. Project Flamingo, on the other hand, takes a different method than other simulations. It includes all kinds of cosmic things, from stars and black holes at the center of the universe to galaxies with very different amounts of gas. From a simple sketch of a landmass, the representation of the world changed over time using a method that was organized in this way. The goal of big projects like Project Flamingo is clear: to figure out why data that doesn't seem to match up with the structure of the universe is causing cosmic conflicts. Differences in measurements like these show that we don't fully understand how the world works right now. If you want to compare these metrics to types of music, jazz and classical are like these metrics. Each has its own style but is still linked. Flamingo tries to bring these different points of view together and help us all understand the universe better. But even though it was complicated, the cosmic strain stayed. This conflict still exists as humbling proof that we haven't figured out a lot of the mysteries in the world. It looks like the world doesn't want to share its secrets with us right now. We get a bigger and bigger set of problems to solve as we add more data points and models to our toolbox, like Flamingo. Every time you find an answer, it brings up new questions, which makes the search never-ending. It shows that our quest to figure out the mysteries of the world is complicated and always changing. In the early 1900s, Edwin Hubble made the amazing finding that the universe is expanding. Since then, our understanding has grown at an amazing rate. The Big Bang Theory, dark matter, and dark energy are just a few of the new things scientists are finding out about the size and shape of the universe. We still have a long way to go, but because of tools like the James Webb Space Telescope and huge projects like Flamingo, we can answer questions and look into mysteries we couldn't even imagine a few years ago.